everyone. Today we'll be presenting to you post-quantum cryptography, the cryptography of the future, something that will come up after quantum computers come in. Let's start with our agenda. We'll go with present-day cryptography first. So you'll see RSA, elliptic curve, all the things which we use today, right? After that, we will go into the second part, which will be, quantum computing and how do they affect present-day cryptography. Then we will delve into securing the future, which is what is the cryptographic researchers doing about it, right? What are they doing about it? Finally, we'll look at Crystal's Kyber. That is a NIST finalist and an algorithm that all of you will be using in the future. With that, let me show our bios. So, yeah, I'm Ritik, and that's Tarun. So both of us are very enthusiastic in this space and read a lot about post-quantum crypto. Apart from that, I have some research articles also in the space. Let's start with a big imagination. Imagine does not mean the John Lennon song. Imagine is, I want you, all of you to imagine. So let's imagine a world where communication is no longer possible. All internet communication is hacked. So what are the three different, very useful use cases, right? We have net banking. So in net banking, basically I have money, but somebody halfway across the world is using my money to buy coffee. Then there's email. CEOs send confidential emails. But suppose there's a scenario where competitors are able to read your emails. Finally, intelligence agencies. Intelligence agencies have include something like CIA, RAW, and all of them have national secrets, right? What if their data is also compromised? So what is that one common thing that ensures security of all of these? The answer is cryptography. So you have two kinds. You have symmetric and you have asymmetric, correct? So in symmetric, you have a common key, and the common key is used both by the encryptor and the decryptor to encrypt or decrypt a message. While in asymmetric cryptography, you have algorithms where you have a public key and a private key, where the private key is with only the owner and publicly shared across the world. And you use the public key to encrypt data, while the private key is the way to decrypt it. So to share the key, right, for symmetric encryption as well, you would need asymmetric to bootstrap and start it, right? So primarily, we have three algorithms that use asymmetric crypto, the ones which we use nowadays. One is RSA, one is Diffie-Hellman, and there is elliptic curve-based variants. And all of them, they rely on a hard mathematics problem. So RSA relies on prime factorization, while Diffie-Hellman and ECC relies on the discrete logarithm problem. So what we say is RSA will remain secure if prime factorization is a hard problem. Similarly, Diffie-Hellman and ECC will remain secure as long as discrete logarithm problem is secure. Can somebody guess what this is? OK, that's a very vague question, my bad. So this is the amount of years it would take for you to be able to crack RSA 2048. To put this number into perspective, and just to tell you, this is called 19.8 quadrillion years. Even I had to Google what you call so many zeros, right? The age of the universe is 13.7 billion years. So we are writing algorithms that would take even more than the age of the universe to crack. That is good, right? RSA 2048. So this is for RSA 2048. Now, over here, you would be able to see security levels. So security level is the amount of computations you would need to take to be able to crack something. So say, for example, RSA with 2048 key size has 112 bits of security. That means it would take you 2 to the power 112 computations to be able to crack it. And as we just saw, that is 19.8 quadrillion years, correct? And the other algorithms, if you look at the ECC part or the Diffie-Hellman part, you would observe the security level is either equivalent or even more. So if it's more, that basically means it will take even longer for you to crack it. So natural question comes, why are we here? Why are we having this talk? The answer is on the top, right over there, quantum computers. With quantum computers, there's a different way of compute. They will revolutionize the way we compute and can solve some difficult problems in an easy manner. And I'd like to stress here, not every problem, but certain problems can be solved much faster using quantum computers. That is why you're here. So before we go deep into this, let's look at Niels Bohr's quote. Niels Bohr is a father of quantum mechanics, one of the fathers, I would say. And we'll look into quantum mechanics after this. And quantum mechanics is truly profounding and shocking. So let's start with Schrodinger's cat, okay? All of you would have heard of it sometime in a physics lesson, or if you watch Big Bang Theory, you would have seen Sheldon explain it to Penny 4 times in one episode. So yeah, let me try and explain it to you again for the 5th time, for those who have watched Big Bang Theory. So Schrodinger's cat basically has a cat, you have a box. You put the cat inside the box and close the box. Now once the box is closed, there is no way of you getting information outside. So there's no way you would know what is happening what is the state of the cat, right? Now you use poison, and you put this poison inside. That breaks at a random time t. So until the poison breaks, once the poison breaks, the cat will be dead. Until it does not break, it's alive, correct? So, but since the box is closed, and there's the poison will break at a random time, until the box is closed, we would say the cat is both dead and alive at the same time, right? Because for us outside, there's no way to understand what is happening and what's the state of the cat. So the cat is in a superposition of alive and dead. Now the only way you would find out what it actually is by opening the box. If you open it, it will be alive or dead. But there's a very interesting concept over here, which is how quantum bits work. So quantum bits can also be in its zeroth state and first state at the same time. Just like the cat is both dead and alive, your qubit or quantum bit can be both 0 and 1. So that gives you a different way of computation altogether. With that, a question comes, what are the 3? So there are 3 primary things that help you, that show how quantum mechanics can help. Quantum computing is different compared to regular computing. First is dual nature. So in dual nature, basically means a quantum entity can both be a particle and a wave. Second is superposition. So classic computers, you have a bit, it's either 0 or 1. In quantum computer, as I just said, Schrodinger's cat, both dead and alive. Similarly, a qubit can be 0, 1, 0 and 1 at the same time. So you see a sphere over there, and it means your bit can be anything over there. Finally, you have something called entanglement. Entanglement correlates to different qubits. So suppose I correlate 2 electrons and distance them apart quite far away, right? Now, if I measure one, I know for sure the other is this. And this is primarily used in quantum key distribution, and does have other applications as well. So after the how, let's look at some applications. If you look at the use cases, you would see applications in chemistry, simulation, communication, algorithms, machine learning, a lot of different use cases, and these are just starting. So you will have many more in the future. Primary quantum simulation, optimization problems, so you would have understood that a qubit can be both 0 and 1 at the same time, right? So definitely there'll be some kind of speed up when you're doing simulation and optimization. Now you might wonder why factorization of large numbers is present there on the list. So some of you may have guessed, RSA depends on this. And as I'd mentioned in the start, if RSA security depends on factorization of large numbers. So if this is an application of quantum computing, what happens to our present-day cryptography? Let's have a look. So these are some news clippings from the present-day world. You can see different universities and different countries claiming different things. Yeah, so I'll move next. So now an important thing comes comparison, right? You have classic computers, you have quantum computers. RSA 2048 has 112 bits of security, and that takes some quadrillion years to crack, which is greater than the age of the universe, so we are safe. Now assume you have a quantum computer that is capable enough and has enough qubits. What would the bits of security change to? As you can see, asymmetric crypto is no longer secure, right? You can see bits of security are just 25, 31. 31 is for RSA 15360. So that is comparatively very less, and it is no longer secure. Even on the symmetric side, you would see AES 128, AES 256 bits of security have halved, but over there you can double the key size and you'll be safe. But asymmetric is a bye-bye. So bye-bye asymmetric crypto. Now, I used RSA as an example, but the other algorithms, which are ECC and Diffie-Hellman, depend on something called discrete logarithm. Prime factorization and discrete logarithm all are solvable by the same algorithm called Shor's algorithm, and that's a quantum algorithm. So if these present-day crypto systems may no longer be safe in the future, what do we do? So all of you would be familiar with this set, right? The NP set, you have polynomial problems, you have NP complete problems, and et cetera, et cetera. So what the quantum computing power gives you is it envelopes the P set and gives you more different problems which you can solve easily. So that's what we call the BQP set. And RSA, Diffie-Hellman, ECC, all of them, the hard problem which they rely on, falls inside this. So it's possible for quantum computers to crack. So what did the crypto researchers do? They found new hard math problems. And now they'll base their security on this. So yeah, OK, if it's outside the BQP set, even it should be safe from quantum computers as well, right? And as you can see, now cryptographers, they have come up with 6 different families. All of them depend on a different hard mathematics problem that we hope is not solvable by quantum computers. We are not sure. And Tarun will specifically speak about lattice-based cryptography. Lattice-based cryptography is one of the more promising ones, I would say, because NIST has a couple of finalists from lattice-based cryptography. And Tarun will speak about Crystal's Kyber as well later.
All right. Can everyone hear me OK? Perfect. So let's look at what a lattice is. What do you see on the screen? I don't know about you, but the gamer in me sees a Pac-Man going on over there. Don't worry about that. It's a bunch of dots that are repeating again and again. So, and we find that these have some properties, such as they are a collection of points, they are regularly spaced from each other, and they extend to infinity. Now, in general, a lattice can be n-dimensional one. But for illustration purposes, we will look at 2-dimensional lattices. Let's see how we can form the lattice mathematically. We start by taking 2 vectors, v1 and v2, also called as the basis vectors. From the origin, we move alongside the direction of these 2 vectors to explore new points. And from there, we repeat this algorithm again. For example, if our basis vectors were represented by 5, 0 and 0, 5, and we were to go in 2 times in the direction of v1 and 1 time in the direction of v2, we would reach to the point 5, 10. So in essence, a lattice can be formed by its basis vectors. It can only contain integer linear combinations. So it can be something like v1 plus v2, v1 minus v2, but not irrational combinations of those vectors. Now let's take a step back and try to see if the same lattice can be formed by more than 1 basis vectors. Here you see that we have taken a different set of basis vectors, 5, 2 and 5, 6, and we are trying to reach to the point 5, 10. Your initial intuition might be that it's not possible to reach, but let me tell you it is possible. If you go 2 times in the direction of the vector v1, you would reach 10, 12. And from there, if you come 1 step back in the direction of vector v2, you would arrive at 5, 10. So what do we understand by this experiment? We understand that the same lattice can have multiple basis vectors. And a basis effectively determines how efficiently we are able to navigate through the lattice. Now, I'm going to speak about the hard math problem that forms the foundation for post-quantum cryptography. The problem goes something like this. We are given with 2 basis vectors, v1 and v2, and we are asked to reach to a point which is on the lattice and which is closest to a given target point. Let's take an example to understand this. Let's say our initial basis vectors are 6i plus 3j and 14i plus 8j, and the target point is 11.6, 4.2. Now, how do we solve this problem? As engineers, everything for us boils down to math. and so we do it. We model this in terms of linear equations. And we have two linear equations with two variables. We solve for x and y, and we round them off because we want to arrive at integer linear combination points. We plug back the original values that we got into the equations, and we find that the closest point is 9, minus 2. Now let's take a retrospective at how we did. You can see that we have our basis vectors, 6i plus 3j and 14i plus 8j, and you have our target point highlighted in green, and you find that the actual point is highlighted in red. Now that's pretty far off from our target, isn't it? Can we do better? Certainly we can do better. Let's do something different this time. Let's take the basis vectors to be 2j and 3i. What do we observe here? We observe that these two vectors are perpendicular to each other. In other words, the angle between them is exactly 90 degrees. These type of vectors are called orthogonal basis vectors. And right out of intuition, if you were to reach to the point which is closest to 11.6, 4.2, if you go 4 times in the direction of the vector 3i, you would reach 12. And if you would go 2 times in the direction of the vector 2j, you would reach 4. So out of intuition, you can say that you will reach 12,4, which is the closest point, right? Now, why is this easy? It's because the movement in one direction is not influencing the movement in the other direction. And so we can conclude that if we have a set of orthogonal basis vectors, it is much easier for us to navigate through the lattice. Let's see if we can do the same using the same math that we used before. So again, we model the system as a system of linear equations. You have 3x is 11.6, 2y is 4.2, solve for x and y, and you round them off, and you plug them in the original equations. And as you see, we have arrived at 12,4. Now let's see how we did in terms of graphical representation. You have our basis vectors again on the screen. You have the target point highlighted in the green, and you have the actual point highlighted in red. You can see that's pretty close, right? So at this point of time, I would like to pose a question to you. This was much easy to solve, right? So what if we could use this to form the basis of our new crypto system? And that's what exactly we did. Let's say that we have a set of good basis vectors which are orthogonal to each other and describe a lattice. Now we treat these vectors as our private key, so we keep them safely with us. Let's say that the same lattice can be formed by a set of vectors which are non-orthogonal and so are bad basis vectors. And we make these vectors as our public key, so they are available to the public to see. Now if someone wants to send data to us, they can just encode it in the lattice in terms of some n-dimensional point and send it to us. And since only we have the good basis vectors, we'll be able to navigate through the lattice easily. Now let's have a look at how hard this problem becomes as the dimensions go up. You have a graph which depicts the dimensions and the number of possibilities. And you can clearly see that as the dimensions go up, the number of possibilities are going up exponentially. And by this, we can say that the difficulty of this problem is related to the dimensions in a direct way. We can also say that in practice, the algorithms that we use have more than 1,000 dimensions. So this factor makes it extremely complex, even for quantum computers, to solve this problem. Because it's just that there are too many possibilities. And to give you perspective, this would give rise to the possibilities which are more than the number of physically observable atoms in this entire universe. So in essence, even though if you move in some of the dimensions correctly, the chances are you will be thrown off in the other dimensions if you don't have a good basis vector. Now let's look at Kyber, which is one of the post-quantum cryptography finalist algorithms. The way it works is you start by taking a secret key, a vector, and you form a set of linear equations. So if you plug those values 10, 82, 55 in the below equations, you would get the right-hand side. And then you see there's a plus minus error which is intentionally introduced to harden the problem. So the system of linear equations becomes extremely hard to solve. The difficulty of this problem has been mathematically proven to be an approximation of the closest vector problem that we just saw. So think of it like something like traveling salesperson problem, indirectly maps to Hamiltonian graph problem in terms of its difficulty. So if someone were to solve this, it means they are able to solve the closest vector problem, which we know till date hasn't been possible. Now let's look at how data exchange happens using this crypto system. You have your classic situation, the actors which we cryptographers cannot live with. We have our Alice on one end, and we have Bob on other end. And let's say that they want to exchange data. Now, Bob would take these public key, the equations, from Alice. And he would encode his message in terms of these equations, either by performing additions, subtractions, or some sort of linear combinations on these equations, and forms a set of new equations. He sends these set of new equations back to Alice as ciphertext. And since Alice has the correct solution to these equations, only she can decrypt it using the private key. And now let's look at how far are we from the future. On the x-axis, you can see that we have the passage of time in years. On the y-axis, you can see the number of qubits that we need to crack present-day crypto. You can see that the estimated number of qubits that we need to crack present-day cryptographic algorithms is constantly going down, while in reality, the number of qubits that we have achieved is constantly going up. And even at their current rate of progression, they are expected to meet somewhere in the near future. Now let's look at some of the practical quantum advancements that have been happening over the time. In 2016, NIST started with a post-quantum cryptographic algorithms call, and researchers from various parts of the world submitted their research to NIST. Over the years, you see that many big organizations take their baby steps or initial steps in the world of quantum computing. You can see that in 2017, Microsoft went public with world's first quantum-oriented programming language called Q#. In 2019, Google invented its first step towards achieving quantum computers by inventing a 53-bit qubit computer that could perform basic additions and subtractions. In 2021, you can see that Azure built its first world-class quantum as a cloud stack solution called Azure Quantum. In 2022, we have a list of finalist algorithms that have been selected as candidates for post-quantum cryptography. You can see that Crystal's Kyber is the one that I just explained you, but we have 3 other algorithms. These 3 other algorithms are used for digital signatures, while Crystal's Kyber is used for public key exchange. Going forward, you see these tech giants making leaps in terms of quantum compute. Notable ones include IBM bringing its first 1,000+ qubit computer called Condor, and Azure launching its quantum elements to help chemists across the world solve complex chemistry problems. And you can see that the adoption of quantum compute is constantly growing up. And I want to tell you a funny story here. Just a day before the presentation, I received a ping from one of my colleagues stating that the lattice-based cryptography that I just shown you has been cracked. I don't know about you, but to me that would be a bummer, right? I don't want to present outdated content. But thanks to us, the author of the paper has done a simple bug in his code and has retracted his findings. So whatever I presented is still safe for the considerable future. So what do we want to conclude here? We want to conclude 3 things. 1, quantum computers are extremely capable in terms of their compute power. Now this is what differentiates them from traditional computers and enables them to push the boundaries to break traditional cryptographic algorithms. And so cryptographers have shifted their focus to look for new hard math problems, out of which lattice-based cryptography is just one of the families that seems promising. And last, we would like to urge you to keep an eye out on the quantum world, because this looks very promising, and even at the current rate at which it is progressing, it seems that these algorithms that we've just seen, we will be using them in the very near future. Thank you.